Hello everyone, today we're going to be going over our system design course today, and today we're focusing on the concept of graph databases. Now, graph databases are designed to handle complex and interrelated data in a way that's more intuitive than traditional relational databases. The key difference is their ability to manage many-to-many relationships. So, able to manage many-to-many relationships. And overall, their dynamic scheme is flexible and is willing to change. Unlike their predecessors in the codicil network model, graph databases don't have strict schemas, and there's a way more flexibility to be able to add in records that can be nested with a flexibility of order, unlike traditional predecessor of codicil, where there needed to be a specific set of order of record types. So overall, there is greater flexibility with graph databases. You can have more parameters, for instance. Such as maybe new ID content, whether name, age, sex. It's very flexible to be able to have those relationships and add them on, such as if we were to give an example of social media networks in particular. So, for instance, friend groups, when one is able to sign on a social media platform and you want to search for your friends, chances are that there is a set criteria already set up in place where focusing on age, school, location, where you're able to find your friends and connect with more people and such. Graph databases have a key application, for instance, in graph databases and use cases. And another major advantage of graph databases over codicil is the lack of mandatory ordering for recording children. Children can be added on dynamically, so children can be added on dynamically. And there is no ordering required. Because we mentioned in the previous series of lectures about codicil, it required a set order in place based on hierarchy, but in graph databases, as well as what we talked about in graph models, graph databases have wider ranges of flexibility. That's the main idea that we're getting in this part for our concept overview. And overall, given the flexibility, they modernize querying by supporting high-level declarative query languages such as Cypher and Sparkle. And we also know that declarative is always focusing on the what, as usual, so the flexibility equals greater support of declarative, also known as the what for querying. And overall, it's pretty hard to be able to, especially focusing on really strict relational databases for site querying, because you have to go through a series of steps, and therefore it will become inefficient if you ever have a computation to be able to search through specific forms of data. And yes, so that's our concept overview for graph databases. And it's just a brief overview. Let's go over our concept example. And now, to solidify our understanding, let's go over our concept example. So to fully understand graph databases' flexibility and power, let's consider a real-life example of a social media platform. In such a platform, users can form connections with other users, join groups, post comments, and interact with other posts. So flexibility provides wide range of functions and added data. And the many-to-many relationships inherit this environment of interaction, like a user belonging to multiple groups or posts being tagged with various topics. It's overall pretty intuitive inside of a graph database. So, just for an example, users interaction with different groups. Or tagging in posts. In a graph database, each user, post, group, and topic could be represented as vertices. As we know from our graph model lecture, we know that graphs typically have vertices and edges. Edges focus on the relationships, and vertices are the subjects. So we have subjects. And relationships. With such, subjects can be users' posts, groups, and the edges for typical graphs are the connections of relationships. And when a new user joins the platform and starts forming connections, their data can be easily integrated without redefining the entire database schema. So easy integration. Searching through this network is equally efficient. If the platform introduces a feature to search for users who belong to certain groups and have interacted with specific topics, a graph database can handle this through simple queries that traverse the network via declarative programming. Declarative statements, easier search. And integration. And searching through this network is overall efficient. If a platform introduces a feature and such, a graph database can handle this through simple queries and traverse the network, irrespective of whether the connections have started in a given state or time. There we go. And now let's head over to our first practice problem. And now to go over our first practice problem, imagine a social networking service that allows users to follow others and engage with a variety of content types. The data system behind it must map intricate relationships among users, their content, and the interactions on that content. So we need to map intricate relationships between the vertices and edges. When we have already determined exactly what our subjects are, along with their relationships, we can map out and construct a graph database to make various queries and such. A graph database overall will be efficient to store and query these complex and intricate data sets. So mainly what we would have to do is that we need to create a graph that represents the following scenario. And so in our pseudocode, what we have done is that we're calling upon a graph database in this case, and we are putting in the relationships that user A follows user B. So we have user A follows user B creates a post. User A likes and comments. User B's post, and user A shares user B's post. Then user C sees it. And so we have pseudocode already over here that already understands relationships. So for instance, we have already highlighted. I'll just number these as well. So once we have already created user A, B, C, and then post as well. So we have a post by user B, and then here we have a relationship that is already set up with our users and our post as well. So we create edges to represent the relationships once we have already created vertices. These are our edges, which dictate the relationship, as we have already known. So this would be considered a vertice. So I'm sorry, this would be considered an edge. This would be considered an edge. Likes and comments, another edge, and then shares. Then user C sees it. So technically, you can say that the edges are also the actions which define the relationships. Yep, and as we know, vertices are the subjects. So that would be users, posts, comments. And so we have already defined that the first thing that we always need to do, let me just put this over here, is that for the graph databases, we need to, let's move over here, create the vertices. The second one is create the edges. Then after we have done so, what we would do is then query, as we see over here, for any extraction of data. So with declarative programming, so we query with declarative programming. To be able to match the user's posts, shares, and creates between the intricate relationships we have already established. And once we have already constructed the following graph, we can query all of our following data that we have already set in place. And so this is just an outline between our first practice problem. Let me just zoom out so we can get a clearer understanding between everything that was just made. 1 second. All right, now feel free to take a screenshot, and now we will move over to our second practice problem. Then for our next practice problem, let's consider a project management tool where users can create project tasks and assign tasks to team members. So we are mapping the relationships between project tasks, assigned users, overall. We can discern, since we're mapping the relationships between the project tasks, and users, we already know that we have the following vertices, which are considered the subjects. And always the edges are relationships. And they are defined by actions. When we have done so, we can already discern, just according to the pseudocode that we have, we can discern the following. So one, we have to consider our number of users. So in this case, we are going to have user D create a project, create project X. The next one being that user D assigns tasks 1 and 2 to user E for project X. And number 3, we would have user E mark tasks 1 as completed, and then we have user F observe the project completion, the project X completion. So we can already see, namely, and when we go over our steps, we always need to know exactly, one, we need to create our vertices, then we have our edges that are over here, then we assign when a task is already completed. So the database's caching queues are already updated because every system design, every system needs a database caching queue to be able to have their data stored and interact. And then we will be assuming a simple rule that each task completes the following progress. Here in this case, we're going to have 50%. For task 1 and 2, we're assuming a simple rule that each task completion has 50% progress, and we're going to update the progress accordingly in our database. And then user F observe project X completion by a query. So we have a query. So vertices, edges, and project progress. And then we already print our following query. So the steps in order to be able to map out all of our following relationships. There we go. So as usual, one, we need to define the vertices, which we already have discerned based on following users, project tasks as well. Then define the edges. And then have status updates and queries. All right, and so yes, so this was our system design course video series on graph databases. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.